Okay, well, good morning and welcome again to EE40. Somehow you brought back the great weather. All summer was grey in Berkeley. So if you went somewhere to the beach or God knows what, then you did well. But now that you're back, we have this wonderful weather, but of course we have to sit in Penn Evans, but hopefully we'll get something out of it. So we're still sort of in sort of an introductory phase, right? And I see from the homework, for some of you this is terribly easy and you're probably just doing busy work, and for some of you it's a little bit harder. Today maybe we'll have the first few bits and pieces that probably most of you don't know. They're not hard, but most of you haven't seen it, so there are a few nuggets that will start to be sort of new. Okay, so we started talking about circuit diagrams, and we also talked about voltages and currents that sort of run around in these circuit diagrams. And of course, very often you want to know what these are. And there are really two ways to figure them out. One of them is maths, and we will figure out how to calculate voltages and currents in circuits. Why do we figure that out? Well, because later we're going to design circuits, and then we want that the currents and voltages and so they have certain values, right? And so we need to figure out how to determine those. But the other way to determine what the voltages and currents are is to simply measure them. And then use an instrument, and here are pictures of a few instruments. These are instruments like the ones that you find in the laboratory. Actually, why do we have different instruments if they all measure voltage? Yeah. What could be the difference between these? Probably price is one of them, right? Why is the one at the top more expensive? Why would you bother paying more for it? Not because the box is bigger, right? It's more accurate, right? So there are different accuracies and so on. And there was also the digital ones, the analog ones. Used to be that the analog ones were the less expensive ones, the digital ones were really, really expensive. Now it's the other way around. If you really want to get a very, very cheap instrument, you can get a useful but not good digital voltmeter for like $5. Okay, but if you want one that you really can rely on, then you need to pay more like $50 for one thing. So a really good one, this one probably about $1,000. You had a question?
I was going to comment on generally people think digital is more useful and it's easier to read, but there are applications in like automotive code checking where we it's much easier to see the needle go back and forth and slightly.
I totally agree, right? I mean, it's like watches, right? At some point, everybody stopped to have a digital watch. Now, the digital watches, they still exist, but most watches are back with their digital inside, but there is actually hand running around. And why? Well, if you want to know exactly the voltage of 6 digits, this isn't going to do it. But if you 3 meters, and you want to just be sure when you're poking around in your circuit that nothing goes out of range, well, you can look at 3 analog meters and suddenly you get a needle that goes wham, all the way to the other side. You can see that even with the corner of your eye. This one here will just blink and flicker, and it will take you forever to figure out, oops, the voltage was too high, the current was too big, and now your circuit's dead. Okay, so anyways, there are different meters, and for different applications you may want to use one or the other one. What do they measure? Well, they're called digital voltmeters, and that's really what they are inside. But then just sort of on the shell of the digital voltmeter, if you add a little bit of extra circuitry, you can make it that it just measures current and resistance, and especially the cheaper ones, they will also measure capacitance and all sorts of things. Most of the time they will invent a number, and sometimes that number may even have to do with the actual value. But the main things you can measure is the voltage, current, and resistance. And if you want to measure other components, usually you'll use different instruments. Okay, so how would you do that? So now we need a little bit of imagination, right? Because this is a circuit diagram, and of course you cannot go with your voltmeter and somehow connect it to a diagram. You have to connect it to a real circuit. So you have to imagine that the blue things, they're actually components somehow in your laboratory, and the green stuff, that's wires, right? And that's maybe a little bit easier to imagine. So suppose that you had a circuit that we now abstracted with this diagram, and you wanted to know the voltage. Well, first of all, which voltage? Well, in a circuit diagram, we would say which voltage by indicating, for example, here we want to measure the voltage V1. So how will we do that? How will we do this with somebody else? You know it. I know you know it. How will we do that? Yeah, straightforward. Good. Exactly. So the voltmeter, we can also give it a symbol. Why do we do that? Well, because it takes less time to draw it. Well, this wasn't a very nice symbol. E, and there must be one side which is plus. Very often it's red, and then we have to take cables, and yes, very often one of them is red, and the plus one's very often red, and then another one is black, and that's usually the minus or common or whatever one, or whatever it's called. And so that's how we can measure the voltage. And of course we can measure the voltage across any kind of a component. Now if we inadvertently connected the voltmeter wrong, we mixed the plus and the minus up, what would happen? Exactly, we'll just get so for example, if with this setup we measure minus 3.6 volts, well, we measure V1 equals minus 3.6 volts, then if we exchange the two wires, we'll measure plus 3.6 volts. Big deal. Why do I say that? Well, because sometimes I get these questions, well, I have this circuit and maybe there are elements in here, there are sources, resistors and so on, and then you wonder, well, now I need to put the plus and minus to indicate which voltage I want to measure, right? And so where do I put the plus and where do I put the minus? I don't know in which direction the voltage goes. Well, I don't need to know, right? If I set it up like this, I just get the same voltage with opposite sides. Big deal. When you make arrows or plus minuses in your circuit diagrams, you're totally free. You choose the direction, and then you get positive or negative numbers. Okay. All right, so it's pretty simple. What's the outlet there? Well, the outlet here means, well, what would... So I'm not suggesting that you do this, and we'll talk about lab safety in a moment, but suppose that you were to connect now this voltmeter to a really high voltage source, for example, power outlet. What would happen? It would explode? Who thinks it would explode? No, it would simply measure 110 volts, that's all. I mean, actually the better ones would measure 110 volts, and the cheap ones depends on how it's set. But generally, voltmeters, you can measure pretty high voltages, and typically sort of 1,000 volts, so it doesn't break. You're in danger way before the voltmeter is in danger. Why? Why is that? Well, you think about it. Is any current flowing through these wires? There shouldn't be current flowing through these wires. If the voltmeter was perfect, there wouldn't be any current flowing through these wires. It's not going to be perfect, so there's going to be a small current flowing through these wires, but hopefully it's so small that it doesn't matter. Well, if no current flowing, then why should it break current? Well, if the voltage is really high, 10,000 volts, so it probably will break, and so something will break down, right? Put voltage across, high enough voltage across the gap, what happens? The spark flies, right? And so that effect then will destroy it. It gets hot and burns up. Okay, but normally when you measure voltage, and that will also apply later for the oscilloscope, which is a much more expensive instrument, maybe $2,000 to $10,000 or so, or even there are ones that cost $100,000. Hey, you could get a wonderful torque with an instrument in a laboratory, but voltage is, you usually can measure pretty high voltage. Destroy the instrument. So there are some exceptions. Okay, so now sometimes you want to measure current, so then you want to measure amps, and so again we have to ask first. We have to ask the question: where do we want to measure current? Well, we have to measure it in some kind of a branch, and let's just pick again arbitrarily. Let's measure this current Ix. How will we do this now? How will we do this? Yes. Okay, connected in series, that's correct. Now I'll put this a little bit more complicated. So So there, if we want to measure current, that current better flows through our ammeter, right? It's got to really go through the ammeter, otherwise how could the ammeter know what the current is? And how do we make the current that is flowing in that wire go through the ammeter? Well, we first have to break the wire, right? And then we have to connect it. Let's say this is the ammeter, which again is going to hopefully have a positive and negative sign somewhere on the box. Then we're going to connect it like this, so that the current Ix now flows through the ammeter. Okay? And then we can make the same field outside and so on. We can put it all the way around, the other way around and so on. To get a minus sign. So now in this case, the whole current flows through your instrument. That's a little bit a different situation. So if you were to connect an ammeter, or use your EVM and configure it as an ammeter, usually a few buttons, so you have to press, so maybe you have to connect your O cable to the input. And then you go and connect it to the outlet. What's going to happen? Probably a fuse blows. So which fuse? Well, it could be the circuit breaker for the for your household current, or it could also be a fuse inside the instrument. Okay? In the laboratory, more likely it's going to be a fuse inside the instrument, but it's definitely possible that you blow one if you simply connect it to the power supply. Probably can deliver 5 amps, and that's, depending on how you set it, that's more than enough to overload the instrument. And then it's say, if I can, I at least protect myself by blowing a fuse. So why does this happen? Well, again, because now, of course, that whole current flows through the ammeter. And in fact, what's the voltage across the ammeter, ideally? It should be 0, right? In practice, again, it should be very small, but it's like a short circuit, the ammeter. And well, if you put a short circuit, a piece of wire just into a power outlet, again, don't do that. Obviously, fuse is going to blow, or the house catches fire or something terrible like that. Okay, so in the laboratory, it also may happen that one of these fuses blows. That happens, well, we try to avoid it, right? Don't do it on purpose, but if it does happen, please let the GSI know. Why? Well, because we're going to fix it. We're going to put the new fuse in. And the next guy in the lab, he would really be happy if the instrument works. Because we always get these complaints. Well, the lab, everything's broken, and so, if we don't know that something's broken, we don't fix it, and then the next person has a complaint. But for that, so help us. The fuse? How does it work? Well, basically, it's something that detects when a very large certain amount of current flows, and then it breaks the current flow. So the simplest fuses you will find, for example, in cars. It's never happened to any of you that suddenly the light or something doesn't work anymore in the car? Never? Wow, either you don't have cars, or you have wonderful cars, or they got better, or whatever. It hasn't happened to me so recently anymore either, but when I was a student, the car that I had at the time, certainly fuses would occasionally blow. So those are little tubes of glass, so you can actually look through, and if you look through them, you will see a wire in there. And depending on the rating of the fuse, it could be rated for 100 milliamps, 1 amp, 10 amps, 5 amps, whatever, you will find that the wire is actually thicker or thinner. In fact, if you go to any car part shop, Gret or whatever they're called, you can go and look for the fuses in the outlet. You will see these little glass tubes that contain these wires inside the glass, and you can see that they're, depending on the rating, they're going to be wider or less wide, and then there are some metal prongs on either side. So those are the very simplest fuses. Of course, you can also have electronic fuses, all sorts of things, like the GFI circuit. These circuits that you have in bathrooms, that where you plug in an electric shaver or so, or a hairdryer or so, they're a little bit of a special fuse. They make sure that the current runs through the right prongs and not somehow through you, by comparing the current that's flowing these prongs and this funny earth prong. We could talk about this once. If you're interested, come to my office hours and look at it. But anyways, these GF5 terminals, those are these breakers that have a little button at the top. So we tested and another one to reset it. Do you know where they were invented? They're all in everybody's bathroom. It's cold, you have to have one at home. Even in a dorm, even more in a dorm. Because sometimes people become, you know what, you don't know where they were invented? Coney Hall. Coney Hall, or electrical engineering. I wasn't there. I wasn't here either when they were invented. Unfortunately, they were invented way, way before they became a commercial success. So the university never made any money from the patent, but you know, they were invented. It's nice. Okay, so a lot of great stuff incidentally has been invented here. Occasionally I will tell you about one of the others. Alright, so ammeters, fuses inside, and so if it doesn't work, maybe the fuse has broken, or if it suddenly stops working, maybe something has happened that broke the fuse, then try to figure out what it was and let the GSI know. We won't complain or so, but then we'll have to fix it. Okay? So now so far we've said how we could measure voltages and currents. Now we need to figure out how we can calculate them. So let's get going on this. So here we have a circuit. We would like to know what the currents are that are flowing. Suppose that I make a sort of a shell that encloses part of the circuit, actually part of the circuit, not in this particular case, but could also contain a few elements. Now, let's go back to the analogy of water flowing in pipes. Suppose that actually the green things, they were not wires carrying electrons, but they were pipes through which water flows. Okay. So let's say here a little flows, here a little flows, and over there 2 liters must flow in, right? There's absolutely no way that you can get a lot of water out of one faucet and the water doesn't go in anywhere else, right? The total sum of water that flows in or out of this black shape got to be 0. It's got to be, because otherwise all the water of all the world suddenly ends up in one place. And when that happens, it's not good either. We've just seen it in the news. So with electrons, this also doesn't happen. We don't suddenly collect all the electrons of the world in a piece of wire or so. So the currents, the total current that flows in or out of this black shape, got to be 0. Okay, so now we can formalize this, and it's actually called Kirchhoff's current law, or KCL for short. So very often we'll say, oh, let's apply KCL to this node, to this part of the circuit. That's what we mean. We mean that, hey, you know, the number of electrons has to be conserved. So how do we now formalize this? Well, we can say, for example, all the currents that leave this black shape, they must sum up to 0. So first we give these currents names, IA. This would be another current, IB, and IC. And then we can say that IA plus IB plus IC is equal to 0. Okay? So now, for example, if I were in the laboratory, of course I could go and measure IA and IB. I wouldn't even need to bother to measure IC. I could use this equation to figure out. Okay? So, and of course I can make other such shapes. Let me try. Does this work? Any other such shape? This time it even contains a circuit element. That's okay. If the circuit element doesn't have some kind of a third terminal here that I haven't shown in my diagram, and current goes through that third terminal. We'll get later to that situation of But for now, we'll simply show all the terminals. Circuit. Then I can make this kind of enclosure. Do you have a question? Okay. Okay, so see, electronics, it's a wonderful thing, but sometimes it's a really painful thing also. So anyways, here we have another one, and now I'll try to, whoever is listening to the tape will have to see. So now I can again list all the currents that are leaving here. So I make this I1 and I2 and I3, and then the sum of all these things. Okay, good. It's actually not loud. There are also all sorts of buttons here. Okay, good. Wonderful. So, all right. So I simply label all the currents that are leaving the yellow shape. Sum them up. I'm not writing the equation again. You can do this yourselves. And the sum must be 0. Right? And so notice that I introduce names for currents just as well. The yellow ones and the black ones. So it doesn't matter that I introduce arrows that go in all sorts of different directions. I just can be consistent, right? I cannot mix. I cannot say IA plus I2 plus I3. They sum up to 0. Well, because IA goes the other way. Or I1. Okay? As long as I'm consistent, I can introduce as many currents. Likewise, Kirchhoff's current, or I can sum up all the currents that leave a node, and the sum must be 0. I can sum up all the currents that enter a node, and the sum must be 0. Your choice. I always use the currents that leave a node, but that's perhaps only that some over the years and some can get habits. It really doesn't matter. Right? And of course, you also can make combinations. You can have some that enter, some that leave, and if you sum it up just right, then you get the right equation. Anyways, it's a little bit more tricky. All right, so that's Kirchhoff's current law. Very, very simple. Works like water in pipes, and it's terribly important. We'll use this all the time. Okay, so here's an example. So a few currents are given here. I1 and I2 are given, and then others are unknown. Ix and Iy, they're unknown, and we want to find these. So now, one of the things in circuits is that there are circuits really, if you think about it, circuits can be horribly complicated. I've seen a billion or more transits. Billion we can't even fathom how much and how complex this is. How can we ever design something like that? Well, the way we do it is we chop the whole problem down in lots of little pieces that hopefully are very, very easy so that we don't make mistakes. And then we group these simple things together. So now, for this to work, we have to be sure that we understand the simple Lego blocks really, really well. Okay? And so it's important for you to understand it. It's important also for me to understand when you didn't understand it, because if I just keep going like a rocket, things are not going to be good for you, right? So for that, let's try something. When we have some little example like that, then I would like that you give the answer, not me, because I know it already, and if I teach myself before the end of the year, it really doesn't do much good. So now I would like this to be that it's not a test. Like, it's not an exam at all. So maybe at the beginning we can have a volunteer, and it should not always be you, all right? And give part of the answer, or if you really don't know the answer, you can ask also a question. That's just fine too. And then pass this on to another person who gives the next part of the answer until we have the final result. Okay? Who would like to volunteer first? Okay, I don't. Okay, let me try to draw this current. The current, the circle would have to include what? Okay, so it includes this. By X by 1. Okay. Here?
Yes.
All right. Fine.
So then the current going out down is I1.
Okay. Made sense to everyone? Alright, so now anybody else? Thank you. Somebody would. Alright. What about that? Okay, so we could, for example, we could make a shape here, right? And then we could write this, and this, and this curve, right? So that would be, let's call this curve how would I call it? IA, IB, and IC. So IA, I know that you did it much more elegantly, plus IB plus IC is equal to 0. Well then, what is IA? Well, IA is really minus I1, right? Because it's just same place but opposite direction. IB is going to be equal to minus IY, and IC is going to be equal to I2. And then you can say IY is equal to I2 minus I1. Did I do it right? Okay. So obviously, like your colleague did, you can do this much more quickly than the way I did that now. But in case you're a little bit confused, or it's the first time you do this, well then, again, draw some kind of a shape. It must be a closed shape, and then introduce arrows for all the currents that, for example, leave that shape, for all the currents that enter the shape, your choice. Write the equation for that, then rewrite with symbols that you actually know, paying attention to the signs, and solve the equation. Yes.
Does the shape have to be around the
No, the shape, it really doesn't matter at all where you put the shape. The shape simply has to be closed. Okay?
So you can draw a shape that doesn't include any part of the circuit and still be a valid shape. It just makes it a trick.
We'll have you teach the class that. Yeah, so for example, you could make this shape also, and then of course the sum of these two red currents, there has to be 0. Yes.
Isn't there like an ideal voltage source inside shape? That's things up for
No, just fine. It's just fine. It's really totally the same as water. If you have any kind of, let's say you had the universe, okay? All the water going in and all the water going out has to be the same, because otherwise we would quickly either run out of water or we would all drown, right? Okay. So obviously at some point, right, if you make the whole universe get sort of a little bit complicated, could you fusion and then water turns into gold and stuff like that? I don't know. But by and large, right, I mean, for the electronic circuits, if we draw the circuit correctly, in other words, every path where current can go is included in the circuit diagram, we can draw any shape. We could also draw this shape, but of course not very easy, right? Okay. More questions? Okay, so the great thing about Kirchhoff's laws is that there are two. There are two, not just one, but it's also not many of them. So the other one is the Kirchhoff voltage law, and that one is just equally useful. And basically, it's the same thing as, again, if we go back to this water system, if we were to look at the pressure. Right? We would, let's say, measure a certain pressure, 20 psi here. Then we go over here, we get, let's say, a pressure drop of 10 psi plus this element. And it's only 10 psi left, and then other one, pressure goes up again, and so on. So, of course, if we go around the complete circle, for example, around this circle, then the sum of all the pressures has to go 0. We cannot start at some pressure and end up and then have a different pressure. Maybe a little bit easier way to think about that is, suppose it's stairs, right? If we go for mountaineering, no matter what path you take, you can go up and down valleys, up and down stairs. So if you go back to where you came from, the amount of climbing and the amount of going down must sum to 0. Right? There is no way if you go back to where you are that you climb 5 meters more than you went down. You got to sum up to 0. Exactly the same thing with voltages. If you go to any circle, the voltage goes up and down and so on, whatever it wants, depending on the circuit you have, but in the end, you end up exactly where you started from. Okay? So, for that, again, we'll have to indicate what our voltages are around such a loop. So, we can call this one, for example, VA, VB, VC, and now, no, they don't. We'll just get to this. So now, as we walk around this circle, we'll have to use a convention. And I use the convention that every voltage that I enter on the minus sign, I introduce with the minus sign in the equation. Every voltage that I enter on the plus sign, I enter with the plus sign into the equation. So let's try it here. Okay? So the first voltage on my circle would be VA. Well, I enter that voltage on the minus sign, so I need to put it a minus VA into my equation. And then the next one would be VB. Well, I'm now here. I enter on a plus sign, so that goes into my equation with a plus sign. And then VC, I enter again on the plus sign, also in the equation, goes also with the plus sign. And the sum of all of these better be 0, otherwise something's terribly wrong in our circuit. Okay? Actually, we couldn't build a circuit where the sum isn't 0. Okay? So, obviously, if you prefer, you can flip all these signs. It's obvious, right? And use another convention. I tell you my convention. In fact, I will tell you a lot of things the way I do it. I find it pretty okay, but very often it just plain doesn't matter. You can do it another way and you get the same result, the right result too. Just do something that you're comfortable with, and that, of course, is correct. Okay? So that's really only. Okay, so, well, here there are some more examples. Again, we would like to, here, given our actually voltages V1, V2, and V3, and we would like to know what the other voltages are, Vx, for example. So, here again, what do we do first? Well, we want to know what Vx is, then first we need to find, here is Vx. Right? And then we want to express it in terms of things that we actually know. So, for example, V1 and V2, we know already. So then we need to draw a circle. And now again, can somebody dictate me the equation that we get going around this circle? Yes. It just doesn't matter. We'll do afterwards a circle the other way around. In the same circuit.
It sums to 0. But you go one way or
yeah. So I guess it's just my hand that I have a harder time drawing this. But if you think about it, what happens if I draw the circle the other way around? All I get, I multiply my equation with minus 1, right? But the equation, of course, still looks. And later we're going to make loops, other loops, and there again, you make the loop whichever one. It's nice, it's very simple. Circuits are simple if you just cut them up into small enough pieces. Hopefully we'll keep it that way. Okay, so you still look a little puzzled. Do you want to try to dictate the equation for this loop? Yeah. So I start here. Yes. X. Vx. Okay, fine. Got it. Okay, now of course we can solve for Vx, that's V1 plus V2. Right? So now which one? The next one is Vy. Where should we draw the loop? Okay, for example, right? Now I do it again the other way around, just somehow that's how my hand works. So how would the equation be like? Okay, and then Vy equals V2 plus V3. And finally Vc. Well, now we could make another Vc. We could make a loop that goes here, here, and here, for example. Then we go through all the voltages that we actually know. Of course, we could also have chosen a different loop, like this one here. That would have been fine too, but then we have to first solve for Vx and Vy. Would have been very difficult, right? But in principle, we get 3 equations, 3 unknowns in this circuit, and we'll have to somehow solve. But here we can do it cleverly, then we don't have to solve it all. So for the red one, again, what would that be? It would be Vc plus V3 minus V1 equals 0. And so V1 minus V3. Okay? Yes. The black one, did I make a mistake? No. We enter plus sign, we enter minus sign, so minus Vy, and then V3 plus sign again. Was this your question, or did I'm not sure I understood your question first. Which equation? The second equation. The black equation is. I just have a difficulty understanding you.
The yellow line is underlining the voltage, not saying.
Yeah. This little this little it's this what confuses you. This little thing here. Was it that was confusing you? Right. So when I look at the V2 for the black one, I enter here. Then I enter here. I enter here again. Okay. Okay. All right. So we're clear. I'm still not sure whether I understood your question, but if you have answered it, then you're fine. Yeah.
On the second line, it looks like the blue negative on the right of the screen.
No. I just do not. We need a bigger screen, okay? Let's petition the universe, but then I need even more tuition. Let's not do that. Huh? Okay, so now this is very easy. Just another convention. Notice we'll when we mark all these voltages, we do this like V1, VA, and so on. And pretty quickly, our circuit diagram starts getting cluttered very much, right? All these pluses and minuses, and we are just on the previous slide, we were confused. There were too many, right? So another way to do that is to say, well, somewhere in my circuit, at one node, I can pick it, any node, I just call the voltage 0, okay? And that's called the common node. So for example, this one, I call the voltage here. That's my reference, okay? So then, at any node, I simply can say the voltage at this node here is, I call it VA. And there it's a convention that what I really mean is that the voltage between VA and here, that is the definition of what VA here really means. Okay? So simply by putting this funny Christmas tree in the circuit, yeah, ground or common or common load is maybe the most formal thing, but ground is another name. Ground is a little bit overloaded because ground has to do something with real ground, right? This ground here, this terminal here that I actually could touch, it is wired correct. Don't do it anyways, but then that one actually is connected to Earth's ground. There is somebody dug a hole somewhere and put it down into the groundwater or so and made a connection to the groundwater. So the Earth's ground is really the same potential everywhere. Yes.
So that common node is reference for voltage zero, not necessarily.
It's just any volt at any node in my circuit here, at any node like VB. What I really mean is the voltage between here and wherever I put that ground signal. And it's really totally up to me where I'm going to put the ground symbol. I could just as well have put the ground symbol here. Okay? And very often it's up to you. You can choose it. And sometimes I put the ground symbol already on the schematic somewhere. Well, then you're stuck. Right? Okay.
But if you have to actually be able to make that ground.
Well, yeah, you know, zero voltage is kind of a bizarre concept. It's like 0 meters above sea level. Well, what actually does this mean? I recently bought a GPS, and I found out that then I got into loading maps on this GPS, and I found out, hey, maps, it's a terrible mess. How do you determine where you are at a certain spot with reference to what? Earth, if it was a nice sphere, a nice circle, ball, then maybe it would be one thing, but in fact, of course, the Earth is a very complicated thing. At least we care about all the ups and downs, and it's some ellipsoid. So there is like 100 different maps for the Earth, 100 different reference systems of where zero is, and so a big mess, very complicated. In the US alone has in its current maps has 2 or 3 different so-called, more than 3 different so-called, it's called a datum. So what is zero for voltage or for altitude or so, it's kind of forget it, so we are not really saying that the voltage there is zero. In fact, this entire circuit could be 100 volts above whatever the Earth's ground happens to be.
You're just saying that in our reference frame, that point is zero.
Okay, so you have another way to put it. Alright, so we really use it just as a convention that now we can say we just write here VC, and what we mean is between here and here, that's the voltage VC. Yes.
The reason is that it's potential is zero there. So if you want to put the charge, you want to right there at the bottom.
Yeah, no, it doesn't really mean that.
Okay.
It doesn't really mean that. That's a somewhat complicated concept of what zero potential actually means. And we would have to get into the ocean also. In fact, I couldn't even give you a lecture about it. We never care about what the absolute potential is. We only care about voltage. Okay. So, but another thing that we do care about, of course, is power. And most of you probably have already heard that power, that's the product of voltage times current. And so if we have somewhere a circuit component, we measured maybe with some meter, the current's 5 milliamps, the voltage is 3 volts, well, the power is 50 milliwatts. Okay, so that was very, very simple. Now comes this just a little tricky thing that we need to pay attention to. So 15 milliwatts, that's the power. But what do we really mean with that power? If you think about it, power could be delivered, or power could be dissipated, right? And now if you have a certain element, like for example a resistor, well, the resistor, probably it burns up power, it doesn't deliver power, so most likely it's, for a resistor, the power, this 50 milliwatts, would be power dissipated. That's okay? Fine. That sort of sounds reasonable. But what about a battery? Well, now already it gets a little bit tricky because a battery, obviously, it can deliver power most of the time. Actually, that's why we have it, right? But some batteries are chargeable, and then while we are charging the battery, is the battery delivering power? Yeah, exactly. Dissipating, or maybe not dissipating, but at least it's absorbing power, right? It's storing the energy, right? And even for the resistor, you have to be careful. You go to the store and buy a resistor with nice two terminals, you will have them in the laboratory, it's in there and so on. Then, yes, it's true, that resistor is only going to dissipate power. You can't go to Radio Shack and tell them, well, give me a resistor that actually delivers power. But you can go to EE40 and you can learn how to design circuits. You can then design a circuit that behaves like a resistor, but it actually delivers power. In fact, the value of the resistor is negative now. So even for the resistor, it's not so clear. That most of the time the power will be absorbed, but sometimes not. And so there are going to be a few trick problems on the homework where, on purpose, I'm making resistors that actually deliver power. And again, why do I do that? Well, I want to make sure that you understand the sign conventions. So what are the sign conventions so you can get this right? So there are two sign conventions. So there is the passive sign convention. And how do we see that it's the passive sign convention? Well, it's because the pluses and minuses of the voltage and the current arrow, they both go in the same direction. Okay, see that? They go in the same direction. And then the convention, then things work out that the power dissipated in that element, x1 is simply V1 times I1. Okay? And therefore the power delivered, well, that's simply equal to V1 times I1, but with a negative sign. Okay? We can call it whatever we want, right? How rich am I? Minus a million, or I can also say how much debt do I have? Well, plus 1 million. I hope it's not true. And you can check my bracket. Okay, so that's the passive sign convention. And for example, for resistors, usually we'll label resistors just like this. That's also a convenient thing we will see later. If we label resistors like this, then Ohm's law comes out the way we know it and we think it should be. And if we label it differently, then Ohm's law should have a negative sign. We'll get to Ohm's law. But so here is the active sign convention. So V2. Now notice that here I make the voltage and the current go in opposite directions. And of course I could have drawn the voltage the other way around and the current the other way around, both of them, and they still would be in opposite directions, and then again I would have active sign convention. Now it's the power delivered that has a positive sign and the power dissipated that has a negative sign. Okay? And so this is very, very simple. You just got to know this, and if you know it, you will get all the right answers, and if you don't know that, you get all the wrong answers. But you know, some things you just need to know.
What
Yes.
is using high speed?
Oh, I mentioned. Okay. So we have 1 more minute. So let's try to quickly get through this. So here we have a voltmeter and an ammeter. Okay, and we want to know what is the power delivered by X1. So now first of all, the voltmeter, that's the voltage V that we measure here. That actually appears across X1. And the current, well, that's the current that goes in this direction, then it doesn't flow through the voltmeter, but it flows down through the ammeter. That's through the ammeter and through X1, so that's the direction of the current that we measure. Okay? So now, what is the power delivered by the component X1? Well, first of all, we have to determine, with the arrows going the way they do in this circuit here, do we have active sign convention, or do we have passive sign convention? Passive, right? And so power delivered for passive sign convention, is it a plus sign or a minus sign? Okay, it's a minus sign, so here we will have minus 5 watts, minus 6 watts, and plus 3 watts. And here, you can try it yourselves. Here you get plus 5 watts, plus 6 watts, and minus 3 watts. And now I'll tell you something that helps you on the homework. On the homework, you have to do one that has many more of these. You calculate all these powers, and in the end, I asked a trick question. I said, what's the sum of all the powers dissipated by all the elements in an entire circuit? It's going to be 0, right? The circuit overall, it cannot create energy or destroy energy or so. That's something very, very difficult to do. I don't know how to do that. So altogether, these powers, they all have to sum up to 0. So it's very simple. In that question in the homework, you just can put a 0, you will get it right, even if all the other answers were wrong. Of course, you can also use that 0 to check that all your other answers actually were correct. Okay? So, see you Friday. And also today I have office hours, and of course all the GSIs, they have office hours. You'll find office hours every day.